far, all we've looked at is the graph of these very simple inverse power functions. What about the graphs of a polynomial over a polynomial, not just a constant over x to a power? What happens when these things get more complicated? Well, let's take a look. Well, coming back to Desmos, I have altered our function just a little bit. Now instead of a over x to a power, it's a over x minus c to a power. So I've added a number inside the function, kind of inside the denominator. And let's see what effect that number has. Now I want to point out an interesting feature of this graph. Right at x equals 0, we have sort of a brick wall here that the graph seems to have come up against, and as it comes closer to that brick wall, it's just turning away and heading either up or turning away and heading down. This line is what we call a vertical asymptote. It is a value of x that has no function value, and it seems to be a value that the graph kind of wants to veer away from. So we have a vertical asymptote when the graph, as it approaches that line, either goes up toward positive infinity or goes down toward negative infinity. The graph of 1 over x squared has one of these vertical asymptotes as well. It's also right in the middle here, and this time on both sides, the graph veers up towards positive infinity. So vertical asymptotes are one important feature of the graphs of rational functions. Let's go back to our graph of 1 over x, and this time I'll make it 1 over x minus 1, or 1 over x minus 2, or 1 over x minus 3. And notice what's happening here. That vertical asymptote is shifting from the left to the right, or from the right to the left. That vertical asymptote is changing where it's at. Well, that's because there's a different value of x that will make that denominator equal 0. So the vertical asymptotes seem to be tied to values that make the denominator equal 0. Same thing is true for 1 over x squared. You can move that vertical asymptote to the right or move that vertical asymptote to the left. It all depends on the values that make that denominator equal 0. So to summarize what we know about vertical asymptotes so far, when we're looking for vertical asymptotes, we want to find x values which make the denominator of our rational function equal 0. Let's analyze each of these functions to determine where we think vertical asymptotes should be. First, we have the function f of x is x plus 1 over x minus 1. So looking at this denominator here, I see the value x equals 1 would make that denominator equal 0. So we suspect there should be a vertical asymptote at x equals 1. Here's the graph of x plus 1 over x minus 1, and we can see that indeed it does look like there is a vertical asymptote at the value x equals 1. So here's that vertical line, and as the graph approaches it from both sides, it either heads up to positive infinity or negative infinity. So at x equals 1, we did see a vertical asymptote. Let's move on to capital F of x. This is 3x minus 2 over x squared minus 3x plus 2. Well, to see what values would make this denominator equal 0, we'd better factor it. And I think we've seen this one factored before. It's x, and 2 times 1, and both of them negative. So we're going to be looking for vertical asymptotes at x equals 2 and at x equals 1. So here's the graph of 3x minus 2 over x squared minus 3x plus 2. And I've had to adjust the window a little bit to make clear what's going on. But we do again see a vertical asymptote at x equals 1 and a vertical asymptote at x equals 2, just what we were expecting. So vertical asymptote at x equals 1, check. Vertical asymptote at x equals 2, check. Incidentally, if you are graphing x plus 1 over x minus 1 on a graphing calculator and you get a graph that looks like this, then you are not entering the function into your calculator correctly. Let's go back to what that y equals looks like. To get x plus 1 over x minus 1, we need to make sure the x plus 1 should be grouped within its own parentheses and the x minus 1 should be grouped within its own parentheses. So the graphs should look like this. This red graph is the correct graph, not the blue graph. Similarly, the way I entered this function into y1 is not going to give me the graph of 3x minus 2 over x squared minus 3x plus 2. This blue graph is not the correct graph. If we want to see the correct graph, we need to group the numerator within a set of parentheses and group the denominator within a set of parentheses, like this. Or if you can use the more advanced features of your calculator to make something look like a fraction, then that is ideal. Hit alpha y equals to see the fraction options for your calculator. Choose n over d, numerator over denominator, and put 3x minus 2 in your numerator and x squared minus 3x plus 2 in your denominator. And we'll see that both the red graph and the black graph will give us the correct graphs for this function. Now let's move on to h of x and see what vertical asymptotes we can find. Well, our denominator x squared minus 6x minus 7, it'd be helpful to have that in factored form. We can factor that as x times x and 7 times 1, make it a minus 7 and a plus 1, and that makes the middle come out to negative 6x. So we might expect to have vertical asymptotes at x equals 7 and x equals negative 1. Let's take a look at that graph. Here's the graph of x minus 7 over x squared minus 6x minus 7, and we definitely see that vertical asymptote at negative 1. Let's move over toward x equals positive 7, and wait a minute, no vertical asymptote. Something unusual going on here. Let's look at a table of values. Notice that at negative 1, where we see that vertical asymptote, our table says that f of x is undefined. We get real number values at x equals 0, 1, 2, 3, 4, 5, 6. But when we get to 7, our table says that the value is undefined. So why isn't our vertical asymptote showing up at x equals 7? Well, let's look a little closer to 7. Let's see what happens at 6.9 and at 7.1. Well, I see y values of 1.26 and 0.0113. At x equals 6.99, I get a y value of 0.1251, and at 7.01, a y value of 1.248. At x equals 6.999, the y value is 0.1250. At x equals 7.001, the y value is 0.1249. Instead of y values approaching infinity or negative infinity as we get closer and closer to 7, what I'm seeing here is that the y values are getting closer and closer to 0.125 on both sides of x equals 7. Here's how to understand what's going on here. As this graph approaches x equals 7, the y value approaches 0.125 from the left-hand side and from the right-hand side. But at x equals 7, our graph is undefined. So it's almost as though there's a little hole in this graph, the tiniest hole that you could imagine in this graph. Unfortunately, it doesn't show up when we graph things on a graphing calculator or sometimes when we graph things on a computer. These little holes in the graph are not easy to find. They don't show up as obviously as a vertical asymptote. So while we had a vertical asymptote at x equals negative 1, we actually have a hole in the graph at x equals 7. And what is it that makes x equals 7 so different from x equals negative 1? Well, here's the key. X equals negative 1 only makes the denominator equal 0. But x equals 7 makes both the denominator and the numerator equal to 0. So to add some more detail to our notes here, yes, when looking for vertical asymptotes, find the x values that make the denominator equal 0. But x equals c is a vertical asymptote if c makes only the denominator equal 0. There is a hole in the graph at x equals c if c makes both the denominator and the numerator equal to 0. Going back to our examples, we have little g of x. The denominator factors as x plus 2 and x minus 2. X equals -2 is going to make both the numerator and the denominator equal 0. So we're going to look for a hole in the graph at x equals -2. X equals +2 makes only the denominator equal 0, not the numerator. So we're going to expect a vertical asymptote to happen at x equals 2. Here's that graph of x plus 2 over x squared minus 4, and we definitely see the vertical asymptote at x equals +2, as we were expecting. At x equals -2, there's not really any obvious hole in this graph. However, if we do look at the table of values, -2 is undefined, just like at +2, the graph is undefined. So even though we can't see it, we should be aware that there is a tiny hole in this graph right at x equals -2, along with this vertical asymptote at x equals +2. So as we look at capital G of x, we notice that x equals +2 will make that denominator equal 0. Now, is this going to be a vertical asymptote or a hole in the graph? If you said hole in the graph, you're right, because the numerator can factor as x plus 2, x minus 2. So the value x equals 2 makes both the numerator and the denominator, both of them equal 0. So we get a hole in the graph. Now you might be asking yourself, what if there's an x value that makes only the numerator equal 0? Is that somehow important? Well, yes. An x value that makes only the numerator 0 will be an x-intercept of the function, or a 0 of that function.